Recording. All right. Are we all good? We can all see that okay? Awesome. All right. Hi, my name is Zach Mueller. I did some research with Dr. John, Dr. Priyaga, and Dr. Devalupalli. And our project was a neural network model to identify relative movements from wearable OS devices. And the purpose of the project was movement tracking's used daily by almost everyone that has fitness-based technology. So, it's in your iPhones, it's in your Android devices, it's in your smartwatches, and from a health perspective, your doctors and physicians will look at this data to try and give you accurate and good advice, but that's only as good as the data that the devices provide. And currently, they're not very well equipped at, identifying when you're maybe running up the stairs or when you're jogging. As we all know, it tends to be a little iffy on those sort of harder problems. And so we decided to go with a creative approach using a technique called feature engineering. We also use neural networks and the FastAI library in PyTorch. FastAI has kind of revolutionized making neural networks applicable to everyone, um, and it's built off of the PyTorch library. Now, when we were getting our data, we essentially set up the problem as getting six individuals to run a series of actions for 1 minute. This was like walking, running up and down the stairs, working at your computer, walking and talking, standing while talking, and then just regular walking. And as you can probably tell, a few of those are very much so almost the same exercise. And so we wanted to pick ones that would be pretty hard to differentiate. The data we chose to collect included the accelerometer and user accelerations, the quaternion and the relative gravitational motion, the pitch, yaw, and roll, the gyroscopic rotations, and the relative altitude. We'll sort of look a little later as to what exactly the model was looking at. But the feature engineering themselves that I mentioned earlier allowed us to make 171 new features off of these 17 or so features that we collected from the Apple Watch. So uh, this included taking the sum of the squares, a rolling mean of the last 20 instances, uh, a relative variance, some root mean squares, and then we also introduced what we sort of call a time step. And the time step is essentially keeping the last second or two of information in the same input. In this case, it was as simple as just keeping that last row as an input to the current row. Now, our neural networks themselves was about a 7-layer model. It had 3 fully connected layers that you can see here, 1000, 1000 by 500, and then this 500 by 6 as our output layer. And each of these linear layers had a linear batch norm and a ReLU activation function. Now, before they get to these sort of linear, fully connected layers, we separated the categorical and continuous variables, and the categorical ones went through this embedding matrix along with what's called dropout, whereas the continuous variables went through just batch normalization. This is something a little bit different than what's been done for, say, random forests, because it's been found that the neural networks respond a bit better to extensive embedding matrices. And so we wanted to try and capitalize on that as best we could. Now, I'm sure you're probably wondering where the categorical data comes into play. Um, when we pre-processed our data, this occurred whenever, say, there wasn't a previous instance of something. It would get filled with a slot of whether it was present or non-present, and this binary information is what was sent to the embedding matrix. Now, in terms of setups, we looked at two loss functions, one which is commonly used, cross-entropy loss, and label smoothing, cross-entropy, which has only been out for the last year or so. Um, we wanted to look at label smoothing because instead of binary or cross-entropy loss, where it's sort of one and done, you either were or you weren't, label smoothing sort of takes iffy um, iffy predictions into account, and so it's more of a sort of smoother approach rather than just simply cutting off yes or no. We also compared two different forms of optimizers, regular Atom, along with a new optimizer called Ranger, which is the look-ahead optimizer applied onto rectified Atom. And then we trained each for about 5 epochs at a learning rate that we found for each model. And so here we have an example of how we would determine the learning rate. We would pick somewhere around 1 e neg 3 here. Now for the results, we looked at first just sort of the baselines, and then adding the time steps in, adding in the feature engineering, and then the feature engineering plus this time step. And at first, we got about 84 to 85% on the test data. Uh, and then after we did the basic time series, label smoothing was able to get a much higher accuracy compared to the cross entropy loss here, which then we further saw when we looked at the feature engineering. And then when we combine the feature engineering and the time series, that sort of difference was, it was still a percent or so, but it wasn't nearly as distinguishable as this almost 10% jump here. And then when we used the Ranger optimizer, we were able to see even better results, but the impact of label smoothing wasn't shown as much. And so you can see that we had about 97.0 here versus 97.8. And then the cross entropy loss and the label smoothing are almost indistinguishable. They're off by 0.3%. And so we further decided to go through and look at the relative percentage improvements by class between Atom and Ranger with the feature engineering. Now this is with label smoothing cross entropy. And what we were hoping to see is look at how the model behaved and what it was looking at a bit differently uh, when we had the different optimizers. And so we saw that there was a 14% improvement when we were looking at at someone who was just standing while talking versus say this 8.5% improvement of someone who is just simply standing. And then we further looked at this with the time step in label smoothing, along with the feature engineering, and we saw a even larger increase in the standing and talking, but not as much improvement everywhere else because, as we saw, these results were very, very similar. Now, sort of a quick sum up of what all this means. So, we sort of saw that the performance of label smoothing was relative to the number of features that were used. So, as our number of features increased, label smoothing was seeing more of an impact, but once we started introducing those sort of time steps with the feature engineering, while there were statistically significant differences, they weren't nearly as large compared to the other results. Uh, this outperformed the previous works on this data set with just random forest, with an 83% is what they achieved. And then, sort of a further idea of where to take this concept would be to say, take the trained embeddings that the neural network has had and combine it with the random forest algorithm and see if that can possibly improve the results, because random forest is a lighter weight algorithm. And so if we can sort of combine the two together, then it's an even faster model, especially whenever we're trying to deploy this on something like an Apple Watch. And then if you wanted to take this research and go apply it somewhere, the feature engineering is based on the last 30 milliseconds. So you would collect the 30 milliseconds, perform the feature engineering based on the training data statistics, and then you would feed this to a model that's either on a CPU or on a GPU server, for instance. Uh, but that is our research. Any questions? So I'll go ahead and stop the recording, maybe.